Hey everybody, tonight we're solving a tau equation, and the tau function just counts all the divisors of an integer. Okay, now the type of integer we're interested in tonight actually is a prime number raised to a natural number power. All right, now I'm going to just go ahead and write the answer and then show you why. It's equal to k plus 1. This is a k. And that's because, and I'll just list the divisors. 1 is a divisor of any integer. Then in this case, p to the first power, p to the second power, and ellipsis p to the k. So that's clearly k plus 1 divisors, okay? 1, 2, k, and then plus 1 right here, right? So that's k. And these are the only possible divisors of p to the k. Otherwise, p wouldn't be prime, okay? So that's simple enough. So this is a simple result here. Tau of any prime raised to a natural number power is k plus 1, and we've listed the k plus 1 divisors, okay? Now, x's function is our indeterminate here, just like any other equation. And so we're trying to show for p prime, this equation has a unique solution. Okay, now, and I just wrote the solution down because it's very, very quickly easy. I mean, it's easy to see that based on this result we just established here, right? X is equal to p raised to the p minus 2. P minus 2 is the exponent. All right. Now, you'll notice here, and I just demonstrated why, we have an understood 1 there. So when you add this 1 to this p minus 2, you get p minus 1. But remember, you have to increment whatever this exponent is. So we get p. Voila. So that is a solution. All right, that is a solution. Now, but we want to show that it's unique. Okay, now notice, folks, that if we chose any other power of p other than p minus 2, we wouldn't get p here, obviously. And it's the same for any multiple of p, which you'll kind of see that on the next step. All right. To verify uniqueness, we're going to assume that our indeterminate x and our solution that we established here are relatively prime. That means they don't have any common factors. Okay. And so that implies that x is equal to q raised to the k power, where q is some prime. Okay. Now, technically, I guess I should say, not necessarily just q to the k, but we should say m, right? Okay, we should put an m in front of this. I think so, yes. Okay, it could be some other multiple. Yeah, I can't. It's not enough just to say q to the k, right? So let's call this m times q to the k, right? Okay. So what we would get right here is that this would be whatever, and let me just write this. I'll write this out a little more precise. I forgot about that when I was doing this. Times t raised to the m, okay, or times tau of whatever m is. All right. Now, y'all, of course, I'd be assuming that m is relatively prime to q, okay? M, let me write this in right here. So, and I just forgot this, folks. So m and q would be relatively prime. Right? You could write x this way, right? So it's going to have some other prime divisor other than p, right? Owing to the coprimality of these two numbers, right? Okay, so this is going to be equal to 1. And so we get t, this is anticlimactic because you see this is p to the first power, right? All right, so that gives rise to this factor of 2. So this is not prime. This expression is not prime, clearly. Okay, it's composite as it can be, right? So it's not prime. And it would have to be prime to be a solution to this equation, right? It would have to be prime to be a solution to this equation. So I'm going to write not prime. And that means the same thing as composite, I think. Okay. Yeah, so I hope this makes sense here. We don't even have to know what the number of divisors of m is. because and this is a little sloppy right here. There should be an M in here, right, folks? I'll write it directly after this now. Okay. But you can kind of see the spirit of this. The M was an oversight on my part, but you can still see that no matter what, you're going to have a composite number here, all right? So that means that we have verified that this is a solution and it is the only solution. Okay, that's all.